All right. Well, hello everyone. So yeah, my name is Aaron, and this is my ACM project. It's the Quantum Computing Workshop Series. And today we'll primarily be focusing on just having an introduction to quantum computing and having y'all build your first circuit, and just learning about the different components of what quantum computing would entail. Okay, so welcome. And just to recap some things that we marketed about the workshop series. So it's going to be open to everyone from any major, and really no background knowledge is required with that in math, physics, or computer science. We'll definitely aim to teach all the concepts that are necessary to complete any of the material that we cover during the workshop. So our workshops happen every Wednesday from 7 to 9 p.m. And they'll span the weeks 5 to 8, or total of 4 workshops. And if you want to spread the word, people who missed workshop 1, there will definitely be ways for them to catch up, and if they would just want to join in starting week 2. Okay, cool. Well, to look at quantum computing as an overarching question, just what is quantum computing, you'll have to start from places where you know the answer to. So we're going to start with what is a computer as an entry question into the field. And while there's definitely many definitions for what a computer might be, some examples, of course, are like the computer or your phone. The next slide. The definition that we'll be using for the scope of our workshops is going to be just going to be something that takes an input and provides an output based off of a series of instructions that we provide to the program, to the computer. Next slide. And those are algorithms. Algorithms are a specific set of instructions that are used to guide a computer to convert an input or desired output. So, next slide. A really important aspect of the algorithms is our ability to classify them. That's specifically on the aspect of their complexity. So this is really important because this gives us a measure of comparison between different programs so that we're able to determine whether or not a solution is more suitable for a problem. Cool. And just to define algorithm complexity one more time, it's going to be how well a program or a solution scales with the size of input, how well it scales with input. So with these graphs, on the x-axis, you're going to have the size of input, and on the y-axis, we have the time taken to solve the problem. So these are some examples of what algorithm complexity might be grouped into. There are some that will do constant time, for instance, outputting the first character in the file. Doesn't really depend on how long the file actually is. You have others that might be linear, like reading in a file, printing it out backwards. And then you have some that are exponential. These are more interesting because these are problems that classical computers don't have a great solution for, because exponential problems grow really, really fast to essentially become intractable and impractical to solve with classical algorithms. So take, for example, the problem of guessing someone's PIN. Given that it's all digits, if you have a 1-digit PIN, it'll be pretty trivial to guess it. 2, it'll take you a while, but you'll probably be able to do it. 3 or 4, write a program. Once you get to 10 or 20, you reach aspects where it'll take months or even longer for your computer or even a supercomputer to solve. Cool. Next slide. So we're going to do a quick example to really show an example of how classical computers fail in one aspect, and to show a place where quantum computing is able to have its own applications. Okay, so we're going to have some quick math problems, and it would be really great if you could just slap the answer in chat. It'll be really, really simple, but you might want to pull up a calculator. So, next time. 3 times 4. You could monitor the chat, that would be great. Cool. 12, yes. 4 times 6, 72. Cool. Next slide. And then once you get to larger numbers, it'll still be fairly easy for your calculator computer to do that. Awesome. Okay. So this next slide is, you can close the chat box, is pretty useful. But let's look at the other way, which is factorization. Of course, we want useful factorization, so don't just factor out alone. Next slide. What are two numbers that output 15? Any of you can also shout it out.
3 and 5.
Awesome. Next. I guess on 143. It's done.
143.
Just glancing, I think it's going to be 11 and 13. I didn't actually saw this, but cool. Next slide. And still, we're remaining like within reasonable sizes of digits, 4 digits, and now you're getting to problems that you probably can't solve just by glancing or not even sure what to Google, perhaps. But yeah, next slide. So this is an example of a problem that is intractable. Prime factorization. So with our modern computer programs, classical programs, it's extremely easy to multiply numbers together, but it is pretty difficult to factor them. And this is true even for the best algorithms that we have. They're actually very, very slow. And as some of you may know, next slide, that is the basis of modern day encryption. So here in the background, you'll see an RSA 768 number, which is just a really long number that can be factorized. But like looking at it, I don't know where to begin with even factorizing that. So just an example, this problem is so difficult that it will take supercomputers like centuries, millennia to solve, to kind of factorize. We can shorten that time by running across more computers, but like still a really difficult, unreasonable amount of time to break it. Okay. Cool. Next slide. Okay. Cool. You can go back a slide actually. So moving a little bit more on this problem. This is a pretty famous example of where quantum computing has a niche, or a theoretical quantum advantage, which we'll define as a problem where quantum computing does it better than modern classical algorithms. So there is actually a quantum algorithm designed to crack like one of these codes within maybe a week, or within a couple of days, something way more reasonable than 2,000 years. And this is like, if you remember, I feel like a lot of you will probably remember, there was a little bit of a craze about this, something like will quantum computing the internet, with our encryption codes, privacy, etc. But we'll get into this in a moment of why that hasn't happened yet. But yeah, just know that there are different problems where quantum computing theoretically does better than classical computing. Next slide. Okay, so continuing with that, here we have this specific problem graphed like this. So you have quantum computers that are currently performing below traditional computers. Even though I just told you that theoretically we have algorithms that will solve it within like a fraction of the times. So why is that? Why have we not reached the point where quantum computing crossing over into quantum advantage? The reason is because the hardware hasn't quite caught up. Specifically, I think for some of these algorithms, you would need somewhere around 100 to 200 qubits, but even the world's largest quantum computers currently are still hovering around like 60 or 70 qubits. And that's like for more simple quantum algorithms. And then there's more that will take even more. Cool. Next slide. So the real question that a lot of people should be wondering is, why does quantum computing do it better? And we'll take a closer look at that. Next slide. So the answer lies in how quantum and classical computers are based on different things. And that's the different physics. So our classical computers are based on classical physics, classical algebra, and our bits are based on physics in this electromagnetic sense, which are, again, classical physics. And then on quantum, what's really important is that it's based on linear algebra and quantum physics, which perform with a different series of rules in classical physics. Cool. Next slide. So we're going to give an example of how much it differs by giving an example of what happens on in the quantum world applied to like macroscopic object. You'll probably have heard of this example. It's going to be Schrodinger's cat, but for those who don't, just wait and see. Cool. Next slide. So one scientist in the past did a thought experiment. Next slide. So say you have a cat, glorious. Next slide. You put it in a box, but it's not closed yet, of course. And you put it with this object. This object is going to be a radioactive element. Next slide. And specifically, after a period of time, it will have exactly 50% chance of decaying. So the reason why it has this 50% chance of decaying, and we can't actually figure it out which side it will be, we can't make any predictions, is because the process of radioactive decay lies within the realm of quantum mechanics. And because of that, it is not possible for us to tell whether the decay will occur. But we know that after some period of time, it will have exactly 50% chance of decaying. Next slide. So we take this object and we make a circuit where if it does decay, the cat will die. But if it doesn't decay, then the cat will live. And we close the lid. Next slide. And we wait patiently. Next slide. So, do any of you know what state the cat is in? So, cool. Okay. Well, according to the laws of quantum computing, slide, the cat is not alive. It is not dead, but it is simultaneously both. Okay. Next slide. Woo. So, definitely quite confusing, right? How can a cat be both dead and alive and yet not be a zombie? Well, next slide. This is the idea of superposition. I just want to emphasize, before anyone gets confused, if you are crazy enough to do this experiment, no, the cat will not actually be alive or dead. This is just an analogy to help you better understand what happens on the microscopic level. So, it doesn't work with macroscopic objects, which are large objects like cats. But if you look, for example, an electron will be able to be in two states at the same time, in the sense of it being able to spin both clockwise and counterclockwise at the same time, which is unintuitive, but it has been observed and has a lot of data that supports this finding. Yeah, so superposition is just this definition of when a quantum system is in multiple states at the same time. Yeah. Next slide. Anyway, these are just some means of other examples of what happens with superposition. Yeah. So while we stay on this slide, I'm going to say one more thing. That's with superposition objects, it's really important to note that when you observe it, its state will change. So what does that mean? For instance, with your cat, as long as the box is closed, it remains in its either alive or dead state. But once you open up the box, you will find either an alive cat or a dead cat. Okay, so let me emphasize this a little bit more with these other examples. So, for example, you have your electron that will behave in a wave. For example, positionally, it might be in this part of an electron cloud with some amount of probability, or it might be on the right side with some different amount of probability. And these different probabilities of where the electron will be is its position width. But once you actually observe and confirm where an electron is, or you attempt to, you will actually observe it and it will be in a specific location. That is how superposition is like measured and then becomes something more concrete and is no longer in a superposition state. That is pretty confusing, but again, just to summarize, what you need to know is a state can be in two states at once. Once you measure it, it'll be in one of those states, depending on the probability distribution. Okay, yeah. If you have any questions, please ask in the chat. And it's totally understandable if you're learning this material for the first time. And also, it is definitely confusing. But yeah, we'll have people in the chat to help answer questions. And if you guys have any questions, feel free to ask. Cool. Let's move on. Okay, next slide. So one thing to note, of course, is that this is like still technically theory. So we're going into the topic of interpretation of mathematical theories. So the math is there, the observations are there. The only question then is to give a theory that explains and fits all your mathematical calculations and theories. So next slide. The specific interpretation that we'll be using is the Copenhagen Interpretation. And this is essentially what I just described, where quantum systems can be simultaneously in different states. And only when it's observed does it collapse probabilistically into one of these states. So, okay, lots of words here. Do your best to take it in. If you have any questions, feel free to ask now. Again. But we'll also be doing more things that build off of this, in which case it will definitely reinforce your understanding. Yes?
Can you go through the four point a little bit?
Yes. Okay. Were you here for the cat example?
Yeah, what the hell that was?
Okay, cool. Okay. We'll have another example. Wait, you go next slide and go back. Okay, go back. Oh, sad. It's in a later slide. But let's take, for example, you have a, if I tell you I have an object here, it is either a 0 or a 1. I don't actually have an object, but it's either a 0 or a 1. And I'll tell you that, actually, I need like something to hide. Okay, pretend in this box, you cannot see the inside of. I have some object. I tell you it's going to be either a 0 or a 1. And there's 50% chance that it'll be a 0, and 50% chance that it'll be a 1. So that distribution, 50% 0, 50% 1, is its probability distribution. Now, if I open this box and take it out, it's going to be either a 0 or a 1, because this amalgamation of 0, 1 doesn't actually exist when you observe it. Kind of confusing, but that's how it will be. But if you repeat this system multiple times, you're like, observe it, and you put it back. You observe it, you put it back. 50% of your observations will be 0, and 50% of your observations will be 1. Does that make sense? So this is just a weird magic object. Cool? You have a question? No? Okay. Fine. Next slide. Okay, we've gone over like quantum physics and how it just differs wildly in rules of the universe from classical quantum mechanics, quantum physics, and classical physics. So yeah, we're ready to introduce the birth of quantum computers. So how did this happen? You essentially just have a bunch of scientists who discovered quantum physics, and then they go, how can I exploit these rules of the universe? And so they did. And again, we now have quantum computers that utilize these very special sets of rules to accomplish what classical computers cannot. Next slide. Okay. I forgot on the statistics, but let's talk a bit about where quantum computers stand today. So yeah, I wish I have a graph to show you, but unfortunately I don't. But yeah, so this is the component that we use in quantum computers. That's going to be, oh, can you help someone? Yeah. Anyway. Okay, well, it is known as the qubit, and it is analogous to the bit within computers, which, if you recall, we'll cover later, but if you recall, the computers are built on zeros and ones. They understand everything as zeros and ones. Quantum computers understand everything through qubits, which we'll explain later how they relate to the zeros and the ones. So, more information about quantum computers today. Some leading companies would be like Google, IBM, and they have really big quantum computers, but they're still less than 100 qubits, for sure, as of right now. But a lot of the quantum algorithms that we have already theoretically designed would take somewhere around 200, some maybe 1,000 to actually run, which is why your bit is still secure for now. Okay, next slide.
They also, the point of this is there's also a lot of errors still in modern quantum computers. So that can be introduced by, like, whenever you scale up to a larger number of qubits, it can be harder to regulate the temperatures. So it has to be kept at a very small temperature, and we haven't been able to do that as consistently. So that introduces a lot of error into just the data and the way it's being read. So that's another limit to modern day quantum computers.
Yeah. So are modern day quantum computers as powerful as quantum computers younger ones, or is it more like in time to
Yeah, if you want to go back to that one slide. Okay, so we have this graph that we put early on, but it's really fun. But yeah, so this is specifically for one problem, but this is actually how it looks for most problems, where currently classical computers, traditional ones, perform better than quantum ones, but they're quickly catching up as the hardware catches up. So we expect to see problems with quantum advantage, which are problems where quantum computers do it better. And we'll also encounter problems that have quantum supremacy, which, taking it one step further, are questions that can only be solved by quantum computers in a reasonable amount of time. Yes?
So you said that you have to regulate qubits using temperature?
Sorry.
So like qubits are like physical things.
Yes. Yeah. So there are actually a couple different specific hardware qubits you can use. So like a lot of they could be electron spins or they could be different isotopes. And so it's actually really interesting seeing how IBM will have different implementation than Sycamore, which is the Google-based one. So it actually depends specifically qubit by qubit. But yes, it is a physical thing. It's not like a digital value that's being stored. It is a physical object that we're looking at because it behaves like a quantum bit. And so you have to have a physical object do that. Yeah. And the other thing I'm going to say is that right now, so we're actually a bit closer than you would think. So Google has their Sycamore chip, which is their quantum computing lab in Santa Barbara, and they claim that they have achieved quantum supremacy but that's been disputed by IBM and some other companies. So it is hotly contested right now on whether or not it has been achieved, but at least it is like a nearer term thing than people first thought it would be. So, yeah.
Cool. Okay. More? Awesome. Anyways, yeah. So they already explained this slide, but the goal is still quantum advantage, and we're still working towards it. And as it has explained, we are getting close, if not already there, but it is complicated. Cool. Next slide. You want to start taking this slide?
Yeah, sure. Yeah. So classical bits are obviously 0, 1. We don't have to go over that again. But so we can use these to encode a lot of different information. So for example, ACM, we can encode this using bits. Same thing with an image. Same thing with other knowledge. It can all be programmed in using bits. So in the same way that we use bits and binary to encode information to be computed on the internet, atoms aren't obviously the building blocks of the universe. However, we can use them in quantum computers to store information similarly to classical bits. And so this is qubits. So you may have heard quantum whatever, people throwing it in front of whatever they can. So if you watch Rick and Morty, they'll just say, oh, the quantum whatever, doesn't matter. Then there's Schrodinger's cat, like we've talked about before in this talk. And then here's a little animation explaining what qubits are. So a qubit is, like I mentioned before, it is inherently a physical object. It could be an electron where you measure its spin. It could be a hydrogen isotope. And it really, but conceptually what it is an object that has a chance of being either a 0 or a 1. So whenever it is spun, it's like if you flip a coin, while it's spinning, you don't know what it is. We can tell what the probability of it is depending on how we flicked it, but we don't know what it is until it finally lands. When it lands, then you can theoretically finally measure. So an example of this is in this, where the two skateboarders could be at any position, but the second you start measuring it, then it has to decide which one to collapse into. And so then it goes from a lot of different information to only one bit of information, which is 0 or 1. And And then whenever it has not collapsed into 0, 1, it is in superposition of both of those states. This makes sense. Yes.
So like, if it's in, like, if I measure it, right, and if it's in, like, 0 or something, I wait for a second, if I measure it again, it's 1, I would like store do that if it's 1. If it goes well, you know,
Yeah.
please don't look at it.
Yeah. So whenever we go over the quantum circuits, you'll see how like it's measured. But essentially, whenever we do this, we're gonna take our qubits and we're gonna perform operations on them, and then there will be a specific point in which we measure it, and that's how you measure the output. So it can change afterwards, but we mainly care whenever we measure it.
So you can say like a qubit like stores a probability of like using the 0 and 1 analogy, like of it being a 0 or a 1.
Right. Yeah.
Okay. So, but it doesn't actually store a 0 or 1. Right? It stores the probability.
Right. At least when it's in superposition, and then so it can like you can set it to be one of those.
Like if you have 100% probability 1,
Right. Yeah.
0% 0.
Sorry, can you re-explain this before?
Right. So the skateboard analogy is there are two just people skateboarding on either point, right? So if you don't look, you don't know where either of them are. But whenever you introduce an observer here, the second image disappears and it has to collapse into one specific skateboarder. Did you still have a question?
Oh no, you
Okay. Yes. Perfect. Next one.
Anyway, so if you take the example of the Schrodinger's cat being both a cat and dead, then this is what we will use to like occasionally through our slides represent it being both 0 and 1 in some combination of that.
So now here's where we go into representation. So qubits are a physical thing, and whenever a quantum computer actually goes about measuring and performing circuits, it interacts with the physical, but you abstract beyond that, and we just have a mathematical representation of what's happening. So, so the way that we store those probabilities of it being either 0 or 1 are called the amplitude. So it will either have, so it has a magnitude, which is amplitude, and in addition to a phase. The phase is timey-wimey, wibbly-wobbly. It's very interesting, but we'll get about that later. Normally, it's represented by complex numbers, but for simplicity, we will keep it between -1 and 1 inclusive. And yeah, next slide.
Okay, so specifically with this slide, I also wanted to point out the purple circles that we have there. So that is one representation of what we've just described with a magnitude and a direction. So your magnitude is going to be how big your circle is, its radius, its diameter, and your direction is going to be that black line, its vector. And this is really useful because it allows us to add different qubit states, different amplitudes to create something that would not be possible with classical things. Like how you have 2 qubits, you added them up, and somehow its amplitude is less. And that's because their vectors are in different positions. Cool. Yay. Okay, we're going to be moving on to a, oh sad, I probably should have given y'all a computer. Could y'all take out your computer, please? Okay, but we're going to move on to a hands-on a little bit, where we'll be using a Google Colab, and we'll just be walking through and having you guys experiment with Qiskit. But yeah, don't worry, it is pretty easy. It won't be hard at all. Okay, wonderful. I do. Okay.
Are there any questions about this?
This link. No, the link. View. Type a link. Done. And URL. Pop. QC workshop. I'll just put QC one. Do work. Sad. QC collab. Oop. Okay, okay, copy. Can I zoom in more? I can't. I can. Awesome. Well, this is the link. Let me know if it works and it brings you to a Google Colab, and if you're able to make a copy. And if you don't want to follow along, or if something goes wrong, we will also have someone be screen sharing and talking over, yeah, the contents of the Google Colab. I'm gonna put this in chat to everyone. Up, up. Checking. Awesome. Okay. Cool. Okay. I'm gonna stop sharing and I'm gonna pass over. Wait, let me also allow people to share. Bam. Cool. Oh, sad. Only host. But let me make you a co-host. Co-host. Okay. And we co-host. Awesome. One more. Okay, already co-host. Okay, glorious. We're gonna have someone on Zoom be presenting. So we'll be experimenting, and if it's too quiet, we'll accommodate and do something about it. But for now, Krista, if you want to take over.
Okay, can everyone see my screen okay?
Okay.
Oh, can you not hear me?
Chris, I think it'd be helpful if you like zoomed in like a lot more.
You better?
Do you have any suggestions, John? Well, it's not working this one, but oh yeah, I did. Want to try again though?
Oh, like reshare.
Yeah, sad. Never mind. It is so quiet.
Huh?
I could pass it off to you for like this workshop, question mark. And then maybe next time I'll have something that's a speaker. Oh, I just feel like it's too quiet.
Can you guys hear? Yeah. Yeah. Okay.
Yeah. I'm so sorry. Okay. Well, we'll make do. Krista, to you.
Oh, do you still want me to present?
I do, I think.
Okay. Well, here is the intro to quantum circuits. And
Oh, wait, before we continue, did everyone who wanted to open up the Google Colab? Cool. And the people on Zoom, just like slap in chat if you a yes or no. Otherwise, we are going to do that. Okay. Okay. Back to you, Krista.
okay, well, the first step is right here. You need to install the Python library Qiskit, and all you have to do right there is just run the code below, and it'll say run anyway. Just do it. Hopefully it won't give any like viruses. Just kidding. But and while that's downloading, we can go ahead and take a look at the next step down here. I'm just gonna like go over it, like scroll to the side. So we're going to start by making the circuit. So this function right here, quantum circuit A comma B, it creates A qubits and B classical bits. And you need the classical bits to measure the quantum bits once the circuit is completed. And to get a good idea of the probabilities, every quantum circuit is simulated and measured 1024 times. And this right here, qc.draw, parentheses, parentheses, draws a diagram of the quantum circuit so we can see the circuit that we've built. And right now there won't be very much to see right here. So if I run this code, it'll create a quantum circuit that is 3 qubits and 3 classical bits. And you can see right here the drawing. Is everyone good so far? Cool. Well, in order to measure qubit A into bit B, you have to use the function circuit.measure A comma B. And if you want to measure multiple bits and qubits, then you can replace them with lists. And the lists have to be the same size. That way it's like an even number of qubits and bits, and they can all match together well. So as you can see right here, where it says qc.measure, and then there's like a list that's 0, 1, 2, and then 0, 1, 2, it measures qubits 0, 1, 2 onto classical bits 0, 1, 2. So if we run this right here, it'll draw the circuit, and then you could play around with the numbers a little, like that, 2, 2. Then it'll look a little something like that. So in this circuit right here, the Q naught is measured into the bit 0 by the M box, where the Q naught wire being mapped to a spot labeled 0 on the classical bit wire. And then if you want to simulate the circuit, you need to import Air Simulator, and it creates a simulator object. So right here, if we run that, it should have imported it. So now you can run this code right here below, and it'll perform the simulation and measure the results. And as mentioned before, it'll run it 1024 times. So right here. Before it had like a big error because I hadn't imported the simulator yet. So that's definitely something to look out for. But yeah.
Do we have any questions? Yes.
So what does the circuit mean and measuring qubits onto possible bits?
Yeah, so like whenever we're saying we have the like quantum circuit, that is essentially like what the algorithm is. So you can take your algorithm and it's represented by gates. On that diagram, you can see you have your 3 qubits, and you can see what gates operate on those. And so you will later see different gates operate on different qubits or only on 1 qubit. And then they're drawn down to that C channel, which is those classical bits. So the quantum circuit is basically like the algorithm that you're creating. And then whenever you measure that, you map that onto classical bits to take the output. Does that make sense?
Yeah. So measuring the quantum bits, the classical bits means we're actually measuring what quantum bits are.
Yes.
Like they go into they get out of superposition.
Yes, yes. So they would collapse at that point. So if they're in superposition before and we measured them, then they would collapse out of superposition and choose to be their 0, 1. In this case, they were all 0 because we hadn't put them into superposition yet.
Yeah.
Yes.
Wait, why are they all 0?
Right.
How do you know they're all 0 on this?
Yeah. Yeah. So whenever just creating the qubits, they'll start out on 0. And then there are different gates. So today is completely deterministic. So we'll get into what that means later. But essentially, there are other gates that you will use, namely the H gate, which we'll talk about later. And those will put the qubit into superposition. So right now, this isn't like very quantum as we're introducing these ideas. But later on, we'll put qubits into superposition, and then it will become more relevant, the ordering to this and measuring of this.
If we do have time, we will go into the H gate today.
Right.
Yeah.
Yeah.
Yes.
I don't understand the meaning of the scenario the last output until now.
Gotcha. I can explain this one. So if you remember the example where I had my box, I told you if I do lots of samples, I'll 50%, 50%. So can you scroll down a little bit, Krista? Well, anyway. So our simulator, where it says Air Simulator, that is the action, the thing that is going to be taking those many samples, and then it'll display how many of those samples were 0s, how many of those samples were 1s. of this specific example, here, super download. I don't know how good your vision is, but it says 3 zeros and then 1024. So 1024 is how many times it took the thing out of the box, how many times it observed the circuit. And then since when we start off, the qubits have 100% probability of being 0, and we're just measuring that, it'll be all 0 zeros. But if we have a different circuit where one of them is in superposition, you'll have 2 different possibilities of what you measure, and with each sample, it'll tell you how many for one probability for the other. Yay! Okay.
Cool. Are we good to move on?
Yep.
Okay. Now for deterministic gates, the first gate that we're going to take a look at is the X gate. And this one basically works like a classical NOT gate where it's essentially sorry, essentially flipping them back and forth from 0 to 1. But in this case, the qubits have probabilities of being 0 and 1. So it'll basically flip the probabilities. So if you have 70% probability of being 1 and 30% probability being 0, it'll switch it so that it's 30-70 the other way. And to code an X gate like this, you're going to do circuit.x qubit or circuit.x list of qubits. So for example, right here, this one will create the quantum circuit of 3 qubits and 3 classical bits. And then you're going to do the name of your quantum circuit, so QC underscore capital X dot X, and then 0, 1, it'll perform X gates on qubit 0 and 1. And then we're going to measure and draw the circuit, so we will run it right here. And as you can see, here's the drawing of the gates representing our quantum circuit. And now that we run the simulation, you can see right here that there are different probabilities instead of the 0, 0, 0 for the 1024 times that we run the simulation. Now we're going to try it ourselves, and we're going to set X underscore bits to the array of bits that you want to apply an X gate to. So right here, you can set it to 0 and 1, and then you can see it works. So go ahead and try it for yourself.
Have it open. If we change that that list of 0 and 1, if you change it into 0, 0, 1, what do you expect our simulation to tell us? So one more time, so in this, you have your X gates, which will invert these which start at 0 into 1 after passing through. If you add a 0, you'll have another one on your 0th qubit, so you have 2 inversions. Yeah, what do you think our sampler simulation will tell us? Okay, so there's 3 bits and 3 measurements, so what do you think they'll be? You're probably right. So we live in them.
No, it's already run.
Oh, okay, yeah, sure. Also, I want to run the simulator on it now, on the bottom. Yeah. Okay. Yeah. So yeah. 0, 1, 0. Awesome. Yes. The dictionary.
I think.
Oh, this one. Yeah. So you can do it.
Yeah, I'd say so in the string of for the key, the first integer corresponds to qubit 0, second integer qubit 1, third integer qubit 2. So in this case, qubit 0 starts 0, is flipped to 1, then flips back to 0. And so that's why it's mapped there. So before it only had 1 X gate, it was 1, 1, 0. And now that the state of qubit 1 of the qubit 0 has changed, it's now 0, 1, 0. Does that make sense? Okay, yeah. And then the colon,
So the first X is qubit reads like the converts.
Oh, okay.
IBM, yeah.
Oh, shoot, yeah.
So everyone does it differently. So some of them do it like the first select the 0 index, and you do the 3, then the last one. So we're just making sure. That's it. But every time.
No, I think I've got it. Right. So please be like the X is the X. That's count.
The is measure, and it's created by someone over there, not measure. So that's when we like, simple and throw it onto a classical bits.
Yes. So what happens if you put an X gate like past the measure? So like how you choose it's like at the first index. What if you put an X gate at the 0? Will it like behave the same?
Oh wait, one more time.
So like how we have like the M
Yeah.
and then once you put an X gate like
Okay. So the question was, what if we put an X gate to the right of your measurement? Wow, it would not change your simulation because you're measuring it before the inversion. But if you add another measurement after that, I'm not really sure we'll be able to see the inversion. But like in our situation right now, if we're adding stuff to it after we measure it, we don't care about it and it won't influence our measurement.
okay.
Yeah. Anything else?
Okay. The next gate that we're going to go over is the C0 gate, which is short for controlled not. And it basically works like a classical XOR gate. So if its two inputs are the same, it outputs 0. Then if they're different, it outputs 1. And the only twist is that when you use these gates, one of your input qubits must be used as the output qubit. So instead of being able to do C equals A, XOR B, like in a normal circuit, you would have to do C equals O, C equals AC naught C, C equals BC naught C to achieve the same behavior. In general, if the source qubit is Q0 and the destination is qubit Q1, then we can say we're using a C0 gate controlled by Q0 and targeting Q1. And the code would look a little something like this: circuit.cx, parentheses, your source qubit, and then the destination qubit. So for example, right here, the source qubit is 2, and then the destination is 2. And this creates a quantum circuit with 2 qubits and 2 classical qubits. Then you would perform the function controlled by 0 for your source qubit and 1 for your destination qubit. So let's run this right here. And then here's the result and the drawing that was created by the simulation. So in this circuit right here, you can see there is an X gate that's applied to Q0, and that changes it from 0 to 1. And then there's the C0 gate that's controlled by Q0, and it targets Q1. So the smaller dot indicates the source, and then the larger X plus, this indicates the destination qubit. So you can see right here, it's moving from 0 to 1. Then when you measure at the end, then you find that all 1024 measurements give both bits being 1. So you can see the result right underneath. So now you can go down here and try it yourself. So right here, I'm going to try adding like another C0 gate. And as you can see, it added another C0 gate right there. Does anyone have any questions?
So, okay, so C0 says, like, we have two qubits, right? And both of them are different, then, like, we store, so we store 0 if they're the same, and we store 1.
And you're storing that, so you're comparing two, you get whether or not it is. You have two qubits, if they're the same.
It has the,
You store 0 and 1.
wait, Krista, could you scroll down to the like truth table for the C0, please? It's scroll down. Yeah, just a little bit more. Keep going. There you go. Oh, there. So yeah, that's the controlled knot. So Q0 is like the control, and Q1 is the input. So it looks at like what the control is, and if the control is on, then it'll flip the input of the. It'll flip the input to the other side. Does that make sense?
Okay, so if you have qubit 0 and 1, and we said qubit 0 is control, if qubit 0 is 1, then we flip the other one, flip qubit 1,
Right.
like where, like to the opposite.
Yeah, to the opposite.
So wait, so even if qubit 1 is 1, we still flip it?
Yes. So if they're both 1, it does flip. I think that, yeah. So it's not like, so if it's like, if it is 1, 1, then it'll flip to 1, 0.
Oh.
Yeah. So this truth table is kind of weird because it has Q1 in and Q1 out because you're changing the second qubit.
Yeah.
And then it's controlled by the.
But like.
Yeah. Okay.
So can we do like C0 with more than just 2 qubits? Multiple qubits, like.
So what do you mean? So like
So like, can you perform this operation like? But like, can you do this operation and then do it like get that result and do something another qubit? So, like, would that be? Like, yeah, either.
So like do them multiple times.
Mm-hmm.
Yeah. So you can do multiple C0 gates in succession with same with the X gates and the Tofoley. Yeah. Okay. Does that answer your questions? Okay. Cool. Yeah. So then I'm doing Tofoley, right?
Sure.
Yeah. All right, Carissa, could you scroll up to the Tofoley? Oh, was Stephen doing
I
Tofoley?
don't know, but like I feel like you'd be louder.
Oh no, Stephen, do Tofoley.
Steven, go ahead. I don't know.
Okay.
Well,
All right. Everyone can hear me, right?
yep.
Oh, do you want me to share screen? Okay, give me a second. All right, light mode time. Sorry guys, I don't know how to set my collab to dark mode. Okay, so moving on, we have the Tofoley gate. Basically, two ways of thinking of this.
Can you zoom in by any chance?
Sure. Actually, is this not working? Okay. Oh, sweet. Okay. So is this good? Just before I keep going.
Yes.
Okay, cool. All right. Yeah, so two ways of thinking of the Tofoley gate. The first one is that it's like an AND gate. So it'll only do something if both of the main inputs are 1. But probably a better way of thinking of it is sort of like an extension on the controlled knot, right? So like what Getty was saying, the controlled knot has a source qubit and a destination qubit, right? And if the source is 1, then it's going to invert the destination qubit. And so the Tofoley gate is going to be similar in the sense that it has 2 sources and 1 destination, and it's going to invert that destination if and only if both of the source qubits are 1. So hopefully that makes sense, but I'll show you in a second. And then if you want to code it, it's just going to be circuit.ccx. So it's like controlled knot. And then you put your source qubits. It doesn't matter what order you put them in, since you're just ANDing them together, and then the destination. And so we have sort of a sample little quantum circuit here. So I'll go ahead and run that and we can see what it looks like. Hopefully it doesn't yell at me. Oh my God. Okay. Sorry, bear with me. Yeah, sorry. I was gonna say something, but I don't have anything to fill the time while I'm doing these imports. Does anyone have a joke?
Yeah. So it's pronounced Tofoley, I believe. So it was
sorry.
its last name, I believe, the person who invented it. It took me a while. I never because you only ever read code, you never try and pronounce it, which is why we end up with horrible names like C++ or Qiskit.
Okay, hopefully that works. Okay, sweet. All right, so you can see the sorry, Getty, can you say that one more time?
No. What? I did say.
The name of the gate. Was I mispronouncing it?
Tofoley. I think you were saying it right. It's
Okay.
we know what you're saying.
All right. So here are the Tofoley gates. You can see the source qubits are marked by these smaller dots, and the destinations are marked by these ones, right? So I did kind of put a few in here just so we could see what it does in different situations. So if both of the sources are 1, then you should invert the destination one, right? So this one will be inverted from 0 to 1, and that gets measured to qubit 0. So qubit 0 is a 1 all the time, as we would expect. If one's a 1 and the other one's a 0, then it shouldn't do anything. So this one should stay as a 0. And it gets measured to bit 1, right? And so as you would expect, that one's 0 100% of the time. And then finally, if they're both a 1 and the destination is also a 1, so you have Q0 and Q1 are both being inverted to a 1 right here, and they're the sources for this gate, which is operating on a qubit that was inverted previously, then it'll invert it back to a 0. And so once again, you can check, just as we expect, this one is 0 100% of the time, right? And so basically, I just wrote that out down here as well. So nothing new there. But yeah, there's sort of a little sample area here where you can just add some gates. I put a lot of qubits and bits there in case you wanted to try different things and measure them. I don't know. Does anybody have anything they want me to type in in here, or should we just move on? Okay, gonna take that as a no.
We have a question.
Oh yeah, question. What's that?
So, like you said, when you're reading the result, the first value is the last possible bit, and the last value is the first possible bit.
Yeah. Yeah, so it's like I don't want to like use a lot of weird terminology. I think this is big endian is what it would be called. Basically, like the largest numbered bit comes first, right? I know Getty kind of said the opposite earlier. I tried to say something in chat. But yeah, whenever you're reading the results, the first bit is like the largest numbered one, and the last bit is always bit 0. Is everyone good with that?
Yep.
Okay, cool.
What but
Wait,
bathroom out and then across.
Oh.
Well, so the woman's is right there. The mouse is on across. Yeah.
Go outside, that way, outside, and then on the left.
Yes.
okay.
Right.
Are we good to go on? Do we want to do this, Aaron?
Yes.
Yes. Was
What was the
sorry.
question?
Are we good to keep going? Should I move on to the adder?
I think so.
Okay, cool. All right. So, as I guess most people with computer science background would know, the gates that are like the classical counterpart of the ones we've talked about are enough to make an adder that basically just adds 2 bits together and keeps track of the result in 2 digits, right? So I put some charts together here. Sorry if they're a little confusing. Let me know if you have any questions about them. Basically, it's just summing up the logic of each of the gates we've gone over. And then this bottom one here is just how an adder should work. So like if you're adding these 2 bits together, then this would be the 2's bit of the result, and this would be the 1's bit of the result. This Tofoley chart here is probably the weirdest one. Basically, it's just what it's just saying is if the two source qubits are not both 0, then the destination will just be left as is, and otherwise it will be inverted. Okay. Yeah, so I guess we can move on. Does anybody want to kind of participate in putting together this quantum adder? Please. We'll take like suggestions for gates to add. Or unless Getty already did it.
So I haven't used like the previous logic we talked about, like the experience in one.
Yeah.
Yes.
It may be.
Just copy this right quick.
Yeah. So
Okay. Actually, oh no, what happened? Ah, wrong circuit.
It's a different uses.
Yeah. Okay, why did it not draw that time? Oh my God, I hate this. Okay, that's okay. Did it overwrite it when I printed?
Yeah, so I don't think you can have the print signal.
Got it. Cool.
But if you just do this, I think it'll print both. Hopefully.
Please, where?
Maybe that is
bruh.
Sorry.
Okay.
Guess we can just slap it in a different code box.
All right. Yeah. All right. It looks like the adder has already been finished. So to anybody who actually like wanted to try to figure it out on their own, not that like a lot of people did. I guess maybe you did. But yeah, if you wanted to figure it out on your own, just like go ahead and delete these before looking too closely at them, and then you can think about it. But right here we have the full working adder, right? So you can see if you're familiar with like normal adders, there's two basically XOR gates, right? And those will, well, I guess this ends up being just one, just because the CNOT gate is a little bit weird. But you have an XOR gate, and that'll be the ones digit, and then you have basically an AND gate, and that'll be the twos digit. And normal adders work pretty much the same way. What are they? Okay, and so you can see right here we added together 1 and 1, and we got 10, which is correct in binary. And if you want to like check that it works on all inputs, you can just like comment out different inversions. So this should be adding 1 to 0. We can go ahead and check that it gave us 1. And then if we add 0 to 0, if for whatever reason you're not sure what that is, we can go ahead and run that code, and it should give you 0 100% of the time. So you can check, not hard to check, I guess, that this is a completely functioning adder. All right. So I guess the next part would be the non-deterministic gates, which for today is just going to be the H gate. Getty, did you want to cover that, or should I keep going?
Yes. So
Okay,
we have a couple. So first off, thank you, Stephen and Carissa. Yeah.
Thank you.
Yeah. So we have a couple more slides to go. Okay, just reload it.
You want to do the HK now or after that?
Probably at the end,
Okay.
so that we can use the. So we're gonna go. So now that we have done the example. Oh shoot! I need to share. Sorry. All right, cool. So now that we have the, we've done the example, we're going to go a little bit more technical. And specifically, we're going to go to how we can represent all the wibbly wobbly, timey-wimey stuff with a bit of math. So kind of a letdown because everything else is really cool, it's just math. But it is very neat math. So the first thing that I'm going to explain is a state vector. So a state vector you can use to encode a lot of different things. So one example could be like if you had a state vector that represented the position of this projector, it would be 0, 0, 0 everywhere except a 1 where the projector would be. However, whenever we're dealing with quantum properties, they usually have probability fields. So if, for example, we treat like a UCLA freshman as X, so this would be a corresponding state vector showing at any one point what the probabilities are that they'd be at any specific dining hall. So 21% chance at study, 39% at period, 0 at beer plate, of course, 21% at feast, and 19% at 1990 at Cafe 1990. And so it basically is just a way for us to store all that state and represent it in a vector. But qubits don't have all these dining halls, they only have 0 or 1. So these are the two states that it can finally collapse into, a 0 state or a 1 state. And this is, we're gonna get into, I won't bore you too much about ket notation, but this is technically ket notation. So that's ket x, so this is ket 0, ket 1. And so that means that we can represent any qubit state, including superposition, by a linear combination of these two state vectors. So a linear combination is just a fancy way. Essentially, we just have the qubit. So the Q represents just any qubit, and it's a linear combination of A and B, and then it can be combined into this vector. And both of those are called the amplitudes. And this really confused me a lot, so I'm just going to put that there in case you column versus row vectors. Yeah, any questions? Cool. So now superposition, of course, is, we talked about it before, when you're in a superposition state, it's not 100% know where you'll end up. So that's what the two different amplitudes represent, is the probability that it will end up in one of either state. It's not, yeah. And so then finally we're going to go, phase is kind of interesting, and I couldn't find a very satisfactory explanation of it. So I myself do not have like as good an understanding of phase as I would like, but a way that I've, whenever you explain a quantum state, you usually have those amplitudes as well as a phase here, which is represented by phi. And so two different states that could be seen as identical will can have different phases. And one way that I've seen people explain it is whether the quarter is flipping around one axis or a different axis, but it could still have the same 50% chance of resolving into a 0 or 1. Yeah.
So like, what difference is phasing? Like, I know there's now views of the circles, right? So like, would phase make a difference in that? Like if you add two bits that are like identical, but they have different phases, would you get something different then?
Yeah, the phases can interfere and like and disrupt each other if they're like
So it's all like phase, well, it's
usually.
So how do you tell it apart that
Yeah, so whenever you quantify like a quantum state, you'll tell the phase by the phi. So what was your question? Like,
so like, well, it's more example of a right like a wave function.
Right, yeah.
So do you tell the wave to be the function of that?
I believe so. I don't exactly know. I know that there's a global phase and things. So then things are usually either in phase with that or out of phase. So, but at least for now, shouldn't have to worry about that.
I'd like to bear that.
Okay.
This is like pretty confusing. So this is it's called a global phase. So relative phase would be two different quantum states with different relative phases that would be different. That would be like the different zero zeroness, that would be like the relative phase. So this is a global phase. So what this is if I have quantum state 1 and quantum state 2, and I measure quantum state 1, like let's say like in and I measure quantum state 2, and mathematically I calculate that they're different. But if I measure them both like an infinite amount of times and they're the same, then they're the same state. If you can wrap your head around that. So like you end up like pulling this like phase and stuff into the I theta or like out of when it got into the math, you end up like pulling this term out in front, and if it has no effect on the measurement, then they're the same. So you can't apply this to everything. It's not every, if I measure two different quantum states in 0 and get 50%, they're not necessarily the same quantum state, they're different relative phases. But it helps once you get into the math. It's basically like a fun term in full.
We might not go into the math of the scope of our workshops, but thank you for the insight.
Thank you.
But this is like very difficult.
Yeah. So at least, yeah. Thank you. And so hopefully we won't be delving in much into that. But whenever we start getting into like the representation with the complex values, then I believe it pulls up, right? So, never mind. So,
before we move on, I also want to give like a little bit of an intuition, like do a phase again. Are any of you familiar with like the physics of the split experiment? No. Yes. Okay. Cool. So I'll just Google it, and then just like show an image on the spot. Double slit experiment images. So when you have a wave and, okay, sad. If you think about, can I expand you bigger? No? Can you be bigger? Please be bigger? Okay, thank you. Okay, so if you have like a dam and you have like a ripple, and you ripple it through one hole, I would love to draw. Oh, sad. Okay, maybe I could. Okay. You could help me just rotate that over. Anyway, so if you have a source that's gonna ripple out, you pass it through a slit. We're gonna say the slit's like this. You have one slit. The pattern of the ripple going through is just gonna look like this. So we're just gonna keep rippling out. And if you do this like with real life, with the water, you'll see that this is true. Now, if make this anyway. Both of them are okay. But if you have two slits now, one here, and your pattern of behavior, if you have like the shore over here, instead of having like a really common ripple where like the side would be, I'll have to demonstrate again exactly how we measure it. But if you have one slit, the strongest waves are going to hit right here, directly opposite the slit. Does that make sense? So following, cool. This is as expected, and we'll get weaker the farther you go. Now, once you add your second slit, what's going to happen is that you're going to have wave interference. So, if you have waves that ripple out, oh, this marker. Yeah, okay. You'll have points where their waves will be much stronger. They'll like add together and become stronger. And you'll have other points where they'll be much weaker than if it were just one slit. So following, okay. So the pattern that you'll see on the wall is something that goes a little bit like strong, weak, strong, weak, strong, weak, strong, weak, etc. Okay, so this is like a demonstration of how waves like interfere with each other, and this principle of how things being in phase versus out of phase, influencing like their output and the measurement, is the same intuition that you would want to apply to your qubits, which is another reason why they're called phases and why it's a wave function and everything. Yeah, but if you do learn about the double slit experiment, you'll have the intuition that like it's another aspect that adding things together makes it a little bit more complicated than just adding two waves together. Okay, back to this.
Constructive and like constructive and destructive.
Yeah, so specifically with qubits, like if the circle drawing that I had, the arrows are in opposite directions and they're like the same magnitude. Maybe not the same magnitude, but if they're in opposite directions, your circle size, the output will be smaller. And if they're in the same size, same direction, the output will be bigger.
Yeah.
Yeah?
Yeah.
Awesome. I'll play it to you.
You put something after this?
I just added the feedback comment.
A what?
Feedback comment.
Oh, the feedback formula. All right, perfect. Yeah. So, yes, thank you. Yeah, so thank you very much for coming by. Our next meeting is next week here, same time. Right. Okay. Next week here, same time. I also, so please fill out the feedback form up here. There's a tiny URL. If you could get to it, that would be really helpful in us to like figure out how to do the flow, and like activities would be more helpful, things like that. Other things, explore Qiskit. Do they have the links to these slides? You can just Google Qiskit textbook. It's really useful. So Qiskit is the software that you did the collab in, and that's useful for quantum for like developing those circuits. And they have a really useful textbook on that. It's a lot of the content that we're covering, and so I'd highly recommend that. As well as when Google claimed they demonstrated quantum supremacy, there's an interesting video on that on YouTube if you want to Google that as well.
Thanks. We're gonna leave the HP for next time.
Yeah. Oh, I think that would make sense to leave it for next time. Yeah.
But yeah, that's it. Before you go, I do have cookies. So
Yes.
you'll have to eat them outside. Hopefully we didn't getting on?
Wait, so what year are you in?
I am a freshman.
And I'm the second year.
How do you guys know so much about this? I feel like I know nothing.
It's the quantum textbook.
Yeah. Qiskit's very useful. And then there's
Yeah, no. I came in with zero knowledge actually about quantum.
Are you a seasoning?
I am.
Are
Right?
you
I am.
Oh, me too.
I knew nothing about quantum like maybe 3 weeks ago. They all yeah. Like that. It's really easy to learn, at least to get your
good.
foot.
Yeah. So grab a cookie. Let us know if you have any questions. We're here to talk. Thank you for coming. Good luck with finals.
Pass this out. I have hand sanitizer and potentially like tissues.
Thank you guys for helping out. We'll see you guys.
I do.
Good luck with everything in midterms.
Yeah.